Welcome to the course on advanced power electronics. So we'll have a lecture 4 on thermal design and DSP applications to power electronics converters. So coming to first cooling and heat sinks. Coming to introduction, for better reliability of electronics equipment, particularly switch mode power supply. An example, thermal management is very important criteria. High temperature component like powered device, electrolytic capacitors, magnetic components, subversive elements, and load condition are major causes of premature failure of switch mode power supply. And failure rate of switch mode power supply double for every 10 to 15 degrees Celsius temperature rise above 25 degrees Celsius. So the layout, size, shape, and selection of component, mechanical and enclosure design, thermal interaction are linked with the thermal performance. The good thermal design and low operating temperatures are crucial for long-term reliability of switch mode power supply. The power dissipation performance must be well understood prior to integrating the devices on printed circuit board to ensure that any given device is operated within its defined temperature limit. When a device is running, it consumes electrical energy that is transformed into heat, and most of the heat is typically generated by switching devices like MOSFET, integrated circuits, etc. So the thermal dissipation, the maximum allowable junction temperature Tj max is one of the key factors that limit the power dissipation capability of a device, and Tj max is defined by the manufacturer and usually depends on the reliability of die used in the manufacturing process. So typical equation used for calculation of ED dissipation is equal to PD max equal to Tj minus Ta divided by theta J, where the theta J is thermal resistance, Tj is junction temperature, Ta is ambient temperature, and PD max is the maximum power dissipation possible by the system. So now coming to heat sink design, the theta J is usually made of at least two separate thermal resistance in series, and one of the thermal resistance inside the device package between the junction and its outside case called theta Jc. The other is the resistance between the case and the ambient, theta Ca, and because theta Jc is under the control of the manufacturer, nothing can be done with it. It is typically low. Another stage can be introduced between the case and ambient, and this is where the heat sink with theta Ca is now split into theta Cs and theta Sa, where theta is the thermal resistance of the interface compound used and theta Sa is the thermal resistance of the heat sink. So typically coming the equation for here, as you see in the heat sink here for thermal resistance, theta S equal to Tj minus Ta divided by Pd minus theta Jc minus theta Cs. As you can see the equivalent circuit, the starting from junction temperature Tj, we have a theta Jc, then it comes to Tc, temperature of casing, then it comes to Ts through theta Cs to surface temperature, and then it comes to the ambient temperature through theta Sa. So in most cases, the Tj, Pd and theta Jc are given in the device manufacturer data sheet, and theta Cs and Ta are used in the defined parameters. The ambient air temperature Ta for cooling the device depends on the operating environment in which the component is expected to be used, and typically it ranges from 35 degrees Celsius to 45 degrees Celsius. If the external airflow through a fan is used from 50 degrees Celsius to 60 degrees Celsius, the component is enclosed, and the interface resistance theta Cs depends on mainly on the interface material and its thickness, and also on the surface finish, flatness, applied mounting pressure, and contact area. And reliability can be obtained directly from the material manufacturer. So with all the parameters defined as theta Sa becomes the required maximum thermal resistance of the heat sink for the application, and thermal resistance value of a chosen heat sink for the application to be equal to or less than the previous theta Sa value for the junction temperature to be maintained or at below the specified. So coming to like a selection parameters, the following are the various important parameters in selecting the heat sink. First, thermal resistance theta Sa, then second airflow, third is volumetric resistance, fifth is the fin density, fourth is the fin spacing, then sixth is width, and seventh is the length. And the thermal resistance is one of the parameters that changes dynamically depending on the airflow available. So airflow is typically measured in linear feet per minute, LFM, or CFM, cubic feet per minute, and LFM is the measure of velocity when CFM is the measure of volume. And typically fan manufacturer use the CFM because fans are rated according to the quantity of the air it can move, and velocity speed is more meaningful for the heat removal at the board level, which is why the derating curve provided by the most power converter, and airflow is either classified as natural or forced convection. And natural convection is a condition with the no external induced flow, and heat transfer depends on the air surrounding the heat sink. The effect of radiation heat transfer is very important, is a natural convention, as it can responsible for approximately 25% of the total heat dissipation, and unless the component is facing a hotter surface nearby, it is imperative to have the heat sink surfaces painted to enhance radiation. And forced convection occurs when the flow of air is induced by the mechanical means, usually a fan or blower. A limited thermal budget or space make the choice of a particular type of heat sink very important, and this is where the volume of heat sink becomes relevant. So the volume of heat sink for a given flow condition can be obtained by using the following equation. Volume of the heat sink equal to volume resistance in centimeter cube per Celsius per watt into Celsius per watt divided by thermal resistance, that is theta, that is per degree Celsius per watt. So available airflow LFM here you can just see the values, and volumetric resistance are given here in the different range, like so. And the same is given graphically here with the air velocity, temperature, heat dissipated, and this also depends on the altitude factors corresponding to where these of course the devices are used. The next important criteria for the performance of heat sink is the width. It is linearly proportional to the performance of the heat sink in the direction perpendicular to the airflow. So considering an example, an increase in the width of heat sink by a factor of 2, 3 or 4 increase the heat dissipation capability by a factor of 2, 3 or 4. Similarly, the square root of the fin length used is approximately proportional to the performance of the heat sink in the direction parallel to the airflow. So in case of an increase in the length of heat sink by a factor of 2, 3 or 4, only increases the heat dissipation capability by factor 1.4, 1.7 or 2. So if the board has sufficient space, it is always beneficial to increase the width of the heat sink rather than the length of the heat sink. And this is why this is only the beginning of the iterative process before the correct and actual heat sink design is achieved. So coming to like heat sink manufacturing process, and that is stamping as a plate, then extrusion, forge, bonding fin, folding fin, sky fin, and die casting. So you can see some of the stamping heat sinks, how do they look like, and then extrusion heat sink, how they look like, and then typically other sets of extrusion heat sink, then the micro forge heat sinks, then the bonding heat sink, then the forge fin heat sinks, then sky fin heat sink, then the die casting heat sink, how it is used with even a small devices. Then coming to heat transfer efficiency and the cost. So heat sink type, here heat transfer efficiency is given typically of different kind of heat sink. So with the stamping flats it's a 10 to 15 watt as a percentage, and probably duct fin bonded goes 78 to 90% typically heat transfer efficiency. And here it is the typically cost versus required resistances. Now coming to thermal modeling of power switching devices. The power generated within the power device increases the device temperature, which in turn significantly affects its characteristic. And for example, the mobility, both bulk and surface value, thirst voltage, drain resistance, and the various oxide capacitance of metal oxide semiconductor transistor are temperature dependent, and the temperature dependence of the bulk mobility causes an increasing resistance with a rise in temperature, thereby the power dissipation. And the device's parameter can affect the accuracy of the transistor model. Therefore, the instantaneous device heating should be coupled directly with the thermal model of the device and heating. So coming to here, electrical equivalent thermal model of complete heat sink. So heat path from the chip to the heat sink can be modeled by one analogous to the electrical transmission line shown here. So thermal resistance and thermal capacitance per unit length are needed for extra characterization of the thermal property. The electric power source represents the power dissipation, heat flow occurring in the chip in the thermal equivalent circuit. So power dissipation, then it goes to the thermal capacitance, followed by the typically thermal resistance one, then second capacitance. So it's a distributed approach, virtually going to the finally the temperature for different parts of the heat sinks. Like so, now the thermal equivalent elements of a typical transistor in a package is solid cooling, temperature that TO 220 or DPAC as shown here, and the thermal equivalent elements can be driven directly from the if the heat inducing area is smaller than the heat conducting material cross, the heat spreading effect occurs here. So you can just see how on the heat sink the temperature variation and the resistance equivalent and capacitance are given here for the different parts of the heat sink material, and typically the formula for the thermal resistance and the junction thermal capacitance given here in terms of the dimensions and material property. So coupling of electrical and thermal components. So coupling of the thermal equivalent circuit with the device model as shown in the figure below for a metal oxide semiconductor field effect transistor can simulate the instantaneous junction temperature. As you can see, typically the device and with the typically the complete thermal equivalent of the different parts, and finally go to the as external heat sinks also from the device to equivalent circuit. Like so, the instance power dissipation in the device, that ID VDS, is determined at all times, and the current proportional to the dissipated power is fed into the thermal equivalence network, and the voltage at node Tj then give the instantaneous junction temperature, which affects directly the temperature dependent parameters of the MOSFET, and the threshold voltage, the drain current, and the drain resistance are scaled according to the instantaneous junction temperature Tj, and drain current IDI temperature is scaled the temperature dependent factor as given by ID at a function of Tj equal to IDI as a function temperature, and Tj upon temperature, that is minus 3/2. Now these are the thermal, and now coming to the digital signal processor or processor which are used for the control of these power electronics circuits, because we have to now we have all these in the processors, the singular processing all these processors. So starting from the microprocessors which are initially used, the main component of central processing unit are the program counter, the instructions register and the instructor decoder, the data address, arithmetic logic unit, the timing and control circuit, and the permanent and temporary storage. A central processing unit on a single chip is called microprocessor, and metal oxide semiconductor MOS and bipolar technology are used in the fabrication process of microprocessor. At present, SCMOS, high-speed complementary MOS or BiCMOS, combination of bipolar and MOS technology to fabricate two microprocessors on a single chip. So the interfacing memory and input-output chips to the microprocessor chips forms a microcomputer, and the pins on each one of these chips are connected to the lines on a system bus which consists of address, data, and control line. And in the past, some manufacturer designed a complete microcomputer on a single chip with limited capability. Now coming to microcontroller, so the microcomputer on a single chip is called microcontroller. The microcontroller are typically used for a dedicated application such as automotive system, home appliances, and home entertainment system. And typically, microcontroller include the microcomputer, timers, analog to digital converter, and digital analog converters, all on a single chip. The examples of typical microcontrollers are Intel 8751 as a 8-bit, 8096 as a 16-bit, Motorola SC 118-bit, and SC16 16-bit, and microchip technology PIC peripheral interface controllers. So now a digital signal processor is typically a microprocessor, one that is incredible, fast, and powerful. And digital signal processor is unique because it processes data in real time, and this real time capability makes the DSP perfect for applications where the delay are not tolerable. Coming to advantage of DSP over the microprocessor, the real time performance, simulation and emulation, and high-speed numbering crunching, flexibility, reliability, increased system performance, and reduced system cost. That's the reason nowadays we use a large number of DSP. So typical example of different kind of DSPs like a TechSci DSP, analog Intel DSP, analog devices DSP are shown as a typically photographs here with a kind of surface mounted. So as a typically some of the DSP manufacturers are Intel, SARC and Cirrus, and TechSci, Instrument, Silicon Hive, then Freescale, Motorola, Qualcomm and LCI, then SARC, WX DSP, Picochip, Mind Speed, SandBridge, Senec, Senelec, AMD, Circus, Ultra, NXP Semiconductor, ARM DSP, KVM, then Tensilica and Siva DSP. So many manufacturers of this. And typical application of DSP like in space application for satellite, and then military applications as military tank and many other. Then the typical application for this in medical imaging and industrial application, then in automotive, then oil exploration, then instrumentation, telecommunication, then control of different kind of devices, then graphics and imaging, then the consumer electronics, then video, voice and speech and computers. And typical application of DSP, of course, if we talk about in control like motor control, disk control, servo control, robot control, laser printer control and engine control. And coming to instrumentation like spectrum analysis, function generation, pattern matching, seismic processing, tangent analysis, digital filtering and phase lock loops. And as industrial like robotics, numerical control, security access, power line monitoring, active noise cancellation and electronics meters. In automotive, like for vibration analysis, anti-lock brakes, anti-skids brakes, engine control, adaptive ride control, global positioning and system diagnosis. And for cellular telephones, active suspension, noise suppression, then electronics power steering, four-wheel steering, airbag control, voice command, and radar detector, navigation, digital radio, and intelligent cruise control. In telecommunication, it is hand-free speakerphone, ADPCM transcoder, digital PBX line repeater, channel multiplexer, 1.256 MB modems, digital speech interpolation, DSI echo cancellation, fax machine, cellular telephone, codeless telephone, adaptive equalizers, answering machine, modems, cable modems, network switching, and data encryption. And for continuing for telecommunication like speech, spread spectrum communication, video compression, multimedia, ISDN basic primary rate interfaces, low speed transcodes and vocoders, DTMF encoding decoding, packet switch and protocol, video conferencing. And for voice and speech application like voicemail, speech vocoding, speech recognition, speaker verification, speech enhancement, speech synthesis and text to speech. And in consumer, for power tools, arcade games, digital audio TV, music synthesizer, educational toys, answering machines, digital video players. And for set-top boxes, digital cameras, features phones, multimedia, karaoke, dishwasher and washing machine. And for graphing and imaging like a 3D rotation, image transmission, compression, pattern recognition, image enhancement, homomorphic processing, workstation, animation and digital map, robot vision. And for military application like secure communication, radio frequency modem, missile guidance, navigation, image processing, sonar processing and radar processing. Now in computer like laser printer, copier, optical character recognition, OCR, neural network, high-speed array processors, imaging, video conferencing, modems, network controller, scanner or barcode scanners. And for general purpose DSP like digital pattern convolution, fast Fourier transforms, adaptive filtering, correlation, Hilbert transform, windowing, waveform generation, discrete cosine transform, and Hartley transforms. Now coming to control applications for motor control, the embedded nature of DSP and the high level of computational power enables the control of the most complicated systems. And today generations of automated systems must be designed with the environment consciousness in mind, with more efficient or power conservation and a more robust control function implementation. And such systems are now possible through the use of digital motor control technology. So typical example of control application as a motor control. We start from the command as a reference profile or move state executive, then go to the controller like as a regulator, then the signal conversion DA to A to D, and then feedback from the sensors, power amplifier, and then motor load or actuator. So this as an example as a digital motor control. So we have a command generation as a polynomial lookup table and control like PID, LQR, Kalman filter, self-healing regulator, model reference, adaptive control, notch filter, fuzzy logic, and gate settling. Then other DSP task is communication control for brushless multi-phase motors, and PWM signal generator for 1 to 3 phase motors, and vector control of induction motor, and system modeling and diagnosis. So motor control systems have traditionally been implemented using analog and passive components such as operational amplifier, resistor, capacitors, and voltage regulator. And alternatively, control may be performed digitally by converting a discrete sample of the analog input signal to a digital equivalent, and the input signal is not processed continuously but is sampled at discrete interval. So a sampling interval of at least 6 to 10 times the bandwidth of the system is usually implemented, and placing a significant performance demands on the system processor. And due to high performance and low cost of digital signal processor and microcontroller, digital motor control system are replacing analog controller in today's designs. So coming to the advantage of DSP based motor control includes the real-time generation of smooth reference and move profiles, integration of memory like a lookup tables and multiple processor into single DSP, use of advanced algorithm resulting in a fewer sensor and lower system cost, like vector control of brushless and induction motor, control of power switching inverters and the generation of high resolution pulse width modulation output, and control of multivariable and complex systems using modern intelligent methods such as a neural network and fuzzy logic. And coming to typically high-end metering with the DSP, so programmability, low power consumption, and the advantage of reduced maintenance and operating cost of the electronic meters are the driving force behind the replacement of Ferrari wheel meters, and DSP are the key features of such system and are suited high features multi-tariff single phase 3-phase meters, and these applications require 16 into 16 bit multiply operators in real time at high sampling rate and to measure the harmonic content of the current. So high-end metering with DSP, a DSP solution based on standard devices is shown here. So we have input signal from UL1, UL3, temperature L3, and measurement 3-phase voltage, 3-phase current, temperature and reference, and measurement signal condition. Then it goes 4 to 8 input, then a MX multiplex DSP, then clock with the DSP TMS 320C2XX, and then we have an interface with the parallel I interface, then serial interface and user interface, and parallel interface may have a display LCD driver EEPROM, and serial interface may be EEPROM, and then it goes to the address data with a parallel function with the control units going to back. So this is a typically basic 320 TMS 320C2XX based electricity meters, as the diagram shown here. So traditional solution with low cost controller will require a 1 microcontroller for each phase, where the single DSP can handle all 3 phases on its own at relatively low clock frequency, and with the spatial scanning and computational algorithm, the power consumption of 3-phase system load can be measured with the minimum error, and system calibration, self-checking, and the setup menu for the system parameter modifications are implemented in software. So in high volume applications, a customizable DSP, CDSP could integrate the interface function of on-chip, and these functions include the LCD drivers, a remote metering reading interface, analog to digital converters, a small card interface, and a external memory interface. And such a single chip solution would result in a low standby currents and improved battery life, thereby reducing maintenance cost. Coming to like a typically control application like laser printer and copier, the TMS 320C6X generation of DSP can turn the office copier into the intelligent document management station, and desktop scanner already have the ability to read a document into the digital form, while the laser printers can convert a digital file into the paper copy, and linking these two machines through a microprocessor produces a rudimentary digital copier. And digital copier enhances the reproduction process by applying digital signal processing technique. Now, by compressing the images and storing them on a disk, the digital copier increases the reliability and simplifies the process reproducing the multiple coated copies, and the use of digital processing for improving on analog and electromechanical methods have existed for some time. However, more revolutionary product will emerge as a advanced image signal processing is applied to do more than the simply copy document. Now coming to DSP architecture, all DSP consists of several fundamental modules like a digital signal processing, core to the perform mathematical operations, memory to store data, and program instructions, a mixed signal product to control between the analog and digital worlds. As a stored program machine, the processor must be told what to do every clock cycle. So typically a DSP fetches an instructions and some data from the memory, opts on the DSP, and then returns the manipulated data to storage. The way this conducted is not the same for all processors. Two different architecture can be identified like von Neumann and Harvard. A typical example is given here how it is WOM architecture like stored program and data and program control, ALU and input, and in case of Harvard architecture like stored program and program output in ALU and with the stored data as a separate side. The architecture of these are shown the architecture of digital process. So von Neumann architecture has set the standard for the computer development over the past 40 years, and both program and data can reside in the same memory mapped space. And the disadvantage with this architecture is that there is only one bus that shares both data and memory address. Therefore, only data space or program space can be accessed in one cycle at any one time. Where the fast data manipulation is vital, accessing both programs and data memory in a single cycle is the advantage. The Harvard architecture separates the program and the data memory spaces, having the two buses to serve each address spaces ensure that the data and program access occurs in parallel, increasing the processing speed. However, the processing power comes with a cost penalty, and two memory spaces require twice as many addresses and therefore the twice as many data pins. So a typical DSP system consists of here DSP chip with the Harvard or von Neumann as a DSP, and then we have a memory as a interface, then A to D converters and D to A converters for interfacing from the outside world or with other processors. So some of the common features of typical DSP systems are a DSP to perform mathematical operations, typically a memory both on chip and external to store data and program instructions, and the third is the convert to signals from analog to digital and digital to analog. So DSP system may require external memory. In practice, the program to be run in normally held in the external memory and then download onto the DSP when the system is started. So this is a typical example of DSP board, how many peripherals on this total JMUL, SL-TOG, then the codec and other peripherals are there as shown here. So coming to the need for speed of DSP technology, the main concern of real-time algorithms is the amount of processing that can be done before a new sampling arrives, and DSP type algorithms are generally of the form involving multiplied and add as A equal to B C plus D. The addition function is quite simple for the conventional computers and can be performed in a single clock cycle. The same is true for the subtraction. Multiply functions takes much longer, especially when considering the numbers such as pi. A general purpose processor may take several hundreds of clock cycles to implement such a calculation. A machine is needed that can perform a multiplied and add in a just one clock cycle, and this requires an architecture molded to the specific application. So the DSPs have a hardware unit within the processor for completing the multiply and add within the single clock cycle, and because such multiply and accumulate MAC instructions are the fundamental building blocks for many DSP application, efficient execution is imperative. Pipelining is an additional method of speeding up the instructions throughput of a processor rather than a speed up the actual time for execute a single instructions. The simplest analogy is that a car production line. It might take 10 hours to assemble a complete car, but because the construction of the car is broken down into many subsections, the car might be finished with every 10 minutes. So computer instructions can be broken down into the stages, so such as fetching the instructions, decoding the instructions, fetching any data, executing the instructions, and storing the result. In a way similar to that, a production line instructions are executed more quickly. The example architecture, the programmable DSP can be categorized into two distinct groups according to their math type, like a floating and fixed point. Floating point and fixed point, these refer to the format used to store the manipulative numbers within the device. So fixed point DSP usually represent each number with the minimum of 16 bit, although a different length can be used. For instance, Motorola manufacture a family of fixed point DSP that use 24 bits, and in the simplest case that the 2 power 16 65,536 possible 4 bit patterns are assigned to the numbers 0 through 65,535. This is called unsigned integer format, and the disadvantage of unsigned integer is that the negative number cannot be represented. So coming to fixed point offset binary, so you can see here the unsigned integer and offset binary is a 16-bit range typically, and 16-bit range. The offset binary is similar to the unsigned integer, except the decimal value are shifted to allow for negative numbers. And in the 4-bit example, the decimal numbers are offset by a 7, resulting in a 16-bit pattern corresponding to the integer numbers -7 through 8. So in this manner, a 16-bit representation would use 32,767 as an offset, resulting in a range between -32,767 to 32,768. The most important use of the offset binary is in ADC and DAC. For example, the input voltage range of 5 volt is mapped to the digital number 0 to 4059 for a 16-bit conversion, -5 volt to 5 volt. Now, coming to fixed point sign and magnitude, how we put it. So here you can just see clearly how we are putting sign and magnitude with the decimal and bit representation for 16-bit range. Sign and magnitude are another simple way to presenting negative integers, and the far left bit is called the sign bit and is made of a 0 for positive numbers and a 1 for negative numbers, and this results in one wasted bit pattern, since there are two representation of 0 like 0 0 0 positive 0 or 1 0 0 0 for negative number. So this encoding scheme results in a 16-bit numbers having a range -32,768 to 677 to 32,767. Now coming to fixed point like a Tooth complement, these first three representations are conceptually simple but difficult to implement in hardware. So remember, when A equal to B plus C is entered into the computer program, some hardware engineer had to figure out how to make the bit pattern representing B combined with the bit pattern representing C to form a bit pattern representing A. The Tooth complement is the format loved by the hardware engineers and is how integers are usually represented in computers. Here typically there is like a decimal and bits representation for. So to understand the encoding pattern, look first at the decimal number 0 in the figure, and which correspond to a binary 0, 0, 0, 0 and 0. As we count upward, the decimal number is simply the binary equivalent 0 equal to 40 or 1 equal to 301 and 2 equal to 0010 and 3 equal to 0011, etc. Now remember that these 4 bits are stored in a register consisting of 4 flip-flops, and if we again start at 40 and begin subtracting, then the bit hardware automatically counts in 2 complement, 0 equal to 40 and -1 equal to 41 and -2 equal to 1110 and -3 equal to 1101, etc. And this is analogous to the odometers in new automobile. If driven forward, it changes 50 to 401, then 402, 403 and so on. When driven back, the odometer changes 5 zeros, then 59, then 498 and then 497, etc. Using 16-bit to complement can represent number from -32,768 to 32,767. The leftmost bit is a 0. Is a 0 if the number is positive, or 0 if a 1 is in the if the number is negative. So consequently, the leftmost bit is called the sign bit, and just as in sign and magnitude representation. Now coming to floating point numbers. In floating point scheme, the basic idea is the same as the used in scientific notation, where the mantis is multiplied by 10 raised by some exponent. And for instance, 5.4321 into 10 power 16, where 5.431 is the mantissa and 16 is the 6 is the exponent. So notice that numbers represents a scientific notation are normalized so that there is only one single non-zero digit left of the decimal point, and this is achieved by adjusting the exponent as needed. So floating point representation is similar to the scientific notation, except everything is carried out in a base 2 rather than base 10. While several similar formats are in use, the most common is NSI, that's IEEE standard 754 1985. This standard defines the format for 32-bit numbers called single precision, as well as 16-bit numbers called double precision. So as shown below, the 32 bits used in single precision are divided into 3 separate groups. The bit 0 through 22 form to form the mantissa, and bit 23 through 30 form the exponent, and then bit 31 is the sign bit, as shown in the here. So 1 sign bit and 8 bit for exponent and 23 bit for mantissa, as shown here, typically of the 32 bit. So these 32 bit form a floating point number V by the following pattern: V equal to -1 to power s into m into 2 to power e minus 127, where s is the value of the sign bit, 0 for positive number and 1 for negative number, and e is the value for exponent between 0 to and 2 to 55, represented by the 8 exponent bit, and subtracting 127 from this number allow the exponent term to run from 2 to power minus 127 to 2 to power 128, and m is the value of mantissa. So mantissa m is formed from the 23 bit as a binary function, and for example the decimal fraction 2.783 is interpreted as 2 plus 7 by 10 plus 8 by 100 plus 3 by 1000, and the binary fraction is 1.0101 equal to 1 plus 0 by 2 plus 1 by 4 0 by 8 plus 1 by 16. So floating point numbers are normalized in the same way as scientific notation, that is there is only one non-zero digit left of the decimal point called binary point in base 2. So since the only non-zero number that exists in the base 2 is 1, the leading digit in the mantissa will always be a 1 and therefore does not need to be stored. So removing this redundancy allows the number to have an addition of 1 bit of precision, and the 32 stored bits referred to by the rotation M22, M21, M20, so on, M0 form the mantissa according to the following equation: m equal to 1 dot m22, m21, m20 to m1. In other words, m equal to 1 plus m22 to the power minus 1, m21 to the power minus 2, and to go to m2, m19 to power 2 minus 4, and so on. So if 0 bits through 22 are all 0, m makes on the value of 1. If bits 0 through 22 are all 0, all ones, m is little bit under 2, that is 2 minus 2 to power 23. And using this encoding scheme, the largest number that can be represented is plus minus in bracket 2 minus 2 to power 23 minus 23 into 2 to power 128 equal to plus minus 6.8 into 10 to power 38. So likewise, the smallest number that can be represented is equal to plus minus 1.0 into 2 power minus 127 equal to plus minus 5.9 into 10 power minus 39. The example of floating point number, here it is shown with the bit. First bit is like for plus or minus, and the 7 bits are shown as a number here, and then the remaining, typically the bit shows like 0.75, that is plus 1.75 into 2 to the power 7 minus 127 equal to plus 1.316554 into 10 power minus 36. So now coming to fixed point versus floating point, all floating point DSP can also handle fixed point number. A necessity to implement counters loops and signal processing from the ADC and going on to the DSC. However, this does not mean that the fixed point math will be carried out as quickly as floating point operations, and depends on the internal architecture. So, for instance, the SARC DSP are optimized for both floating point and the fixed point operations and execute them with the equal efficiency. And the internal architecture of floating point DSP is more complicated than the fixed point device. All the register and data buses must be 32-bit wide instead of only 16-bit. The multiplier and arithmetic logic unit must be able to quickly perform floating point arithmetic, and the instruction set must be larger so that they can handle both floating point and fixed point number and so on. So floating point 32-bit has a better precision and a higher dynamic range than the fixed point of 16-bit, and floating point programs often have a shorter development cycle since the programmer does not generally need to worry about the issues such as overflow, underflow, and round of error. And a fixed point DSP have traditionally been cheaper than the floating point devices. So various type of DSP TMS family like F4X and C4X, and typically DSpace 1104 oblique 1103 controller, micro-loopback, ADMC 401326, and FPGA, Verilog, and VTCL, and OpenRT. So coming to first TMS 320 family overview. The TMS 320 family consists of 16-bit fixed point, 32-bit floating point, and 64-bit microprocessor single chip DSP. And these processors have the operational flexibility of high-speed controllers and the numerical capability of array processors. And combining these two qualities, the TMS 320 processors are inexpensive alternative to the custom fabricated VLSI and multi-chip bit slice processor. So the following characteristic makes TMS 320 family the ideal choice for a wide range of processing applications like flexible instruction set, inherent operational flexibility, high speed performance, and innovative parallel architecture and cost effectiveness. So in 1982, Texas Instruments introduced the TMS 320 1X, the first fixed point DSP in the TMS 320 family, and today the TMS 320 family consists of the following generation like 1X, C1X, C2X, C3, C20X, C24X, C5X, C54X, and C62 into C2X 16-bit fixed point, and C3X, C4X, and C67X 32-bit floating point, and C8X 16-bit multiprocessor. And this is the family, the TMS family road starting from C1 or 2X to control optimization for power efficient performance, and then for high performance computing. Now each generation of TMS 320 devices have a similar architecture, a CPU combined with a variety of on-chip memory and the peripheral configuration, and new combinations of on-chip memory and the peripheral options are used to create spin-off devices that satisfy a wide range of needs in the worldwide electronics market. So when memory and peripherals are integrated into one processor, the overall system cost is greatly reduced and board space is saved. So typical example, 320 device naming convention like TMS 320, the device family name, and prefix here TMS4, SMJ, all these are defined, and C is for technology, I mean what you do, CMOS technology or any other, and 25 is the typically for the generation like 1X also, as you can see here, and then FN L40, and similarly for this is for another FN family. This is for, so the key members by generation of TMS 320 family are TMS 320 C2XX generation, TMS 320 CX 3X generation, 4X generation, 5X generation, 54X generation, 6X generation, and 8X generation. Now coming to 320 C2XX generation, TMS 320 C203 is a fixed point 16-bit DSP with 544 words of on-chip RAM and 2 serial ports that runs up to 80 MHz, pin compatible with the F206, and TMS 320L C203 is a low power version of the C203, and TMS C26 is a 16-bit fixed point DSP with 4.5 kilo watts on chip RAM and 30 watts with the ROM, and 320 TMS 320F206 16-bit fixed point DSP with 4.5 watts of on-chip RAM, 32 kilowatts on the chip flash memory, and 2 serial ports that runs on a up to 80 megahertz and pin compatible with that C203 and C205. So coming to this TMS 322X extension, this is TMS 320L LC206 low power version of C206 and TMS 320C209 16-bit fixed point DSP with the 4.5 kilowatts on chip RAM and 4 kilowatts of ROM that runs on up to 57 megahertz, and TMS 320C240 is a 16-bit fixed point DSP with the optimized event manager dual on-chip 16-bit analog to digital converters, SPI and SCI ports, 16-bit words of RAM, 28 bidirectional input-output pins, and the watching watchdog timer. TMS 320F240 is a 16-bit fixed point DSP that an optimized event manager, dual on-chip 16-bit 10-bit analog to digital converter, SPI, SCI port, 16 words of the flash memory, 28 bidirectional input-output pins, and the watchdog timer. And TMS 320C241 is 16-bit fixed point DSP with the 544 words on a on-chip RAM, 8 kilowatts of the on-chip RAM, event manager, 10-bit A to D converter, and SCI and SPI ports, and controller area network CAN module. Now coming to TMS 320F241 16-bit fixed point DSP with the 544 watts of the on-chip RAM, 8 kilowatts of flash EEPROMs, event manager, 10-bit analog to digital converter, SCI, SPI ports, controller area network CAN module, and TMS 320C240 is 16-bit fixed point DSP with 554 watts on chip RAM, 4 kilowatts on chip RAM, event manager module, and 10-bit analog to digital converter. And TMS 320F243 a 16-bit fixed point DSP with the 544 watts of on chip RAM, 8 kilowatts of flash EEPROM, event manager, 10-bit analog to digital converter. TMS 320C30 a 33 million floating point operations per second MP of 33 megahertz 32-bit floating point DSP with 2 memory expansion buses, 2 serial ports, on-chip RAM, 2 kilowatts of on-chip RAM, 1 channel DMA and CMOS technology, and TMS 320C31 similar to the C30 with the 1 memory expansion bus, no on-chip RAM, 2 kilowatts of the on-chip RAM, 1 serial ports, a boot loader, and a 1 channel DMA. And the TMS 320L C31 a low power version of the C31. Going to TMS 323X generation, so TMS 320C32 is the lowest cost version of the C3X with the flexible memory interface, 512 watts of the on-chip RAM, low power modes, a bootloader, and 2 channels of DMA with the configuration priority. And TMS 320LC32 a low power version of the C32. TMS 320C40 a high performance 330 MPS 384 megabytes 32-bit floating point multi-port parallel processing digital signal processor, and TMS 320C44 a lower cost version of the C40 with 4 communication ports and a smaller address reach. So TMS 320C50 a complete system on a single chip with 2K 16-bit words boot ROM and 10K to 16-bit words on a chip RAM. An entire DSP can be integrated into a 132-pin plastic quad flat pack PQFP, and TMS 320LQ50 is a low voltage version of the C50 3.3 volt power supply, and TMS 320C51 is the C51. The C50 10K volt block of RAM is replaced by 8 into 16-bit word ROM. This provides a considerable advantage in cost and performance for the users who require large amount of on-chip program space. TMS 320LC51 a low voltage version of the C51 3.3 volt power supply, and TMS 320C52 a superb combination of both low cost and high performance register devices in the same price range have offered a 10 million instructions per second MIPS performance, and the TMS 320LC52 a low voltage version of C52 3.3 volt power supply and TMS320C53 provides even greater integration of on-chip ROM than the C51 with a 16K 60 watt on a chip RAM and 4K 16 watts on chip RAM. An entire DSP system can be integrated into a 132 pin PQFP. So TMS320C LC53, a low cost version of the 53 3.3 volt power supply, and TMS320C53S, similar to the C53 specification with the exception of the low 2 standard serial port, the 100 pin thick quad flat pack TQFP, and the pre-programmed ROM, and TMS320LC53S, a low voltage version of the C53S 3.3 volt supply, and TMS320C56, a 3.3 volt device with the 32 kilo 16-bit on-chip RAM and 7K 16-bit on-chip RAM integrated on a 100-pin TQFP. The communication ports consist of a standard serial port and buffered serial port, basically available at 35 or 25 nanosecond cycle time. So TMS320LC57, similar to the LC56 with the additional peripheral host port interface HPI and the 128-pin TQFP, and TMS320BC57S, a 5 volt device, a 2K 16 watt boot ROM and 7K 16-bit on chip RAM. The communication ports are similar to the LC57 and the consist of a standard serial port and a host port interface and the buffered serial port. TMS320C541, available with the instruction cycle time of the 25 nanosecond for 5K watts of RAM and 28K watts of ROM and a 5 volt power supply. TMS320LC541, a low voltage result of the C541, available with the instruction cycle times of 25 or 20 nanosecond with 3.3 volt power supply. And TMS320C542, available with the instruction cycle time of 25 nanosecond for 10K watts of RAM and 2K watts of the ROM and a 5 volt power supply. And TMS320LC542, a low voltage version of C542, available with the instruction cycle times of 25 to 20 nanosecond and 3.3 volt power supply. Now coming to TMS320LC543, available with the instruction cycle time for 25 to 20 nanosecond, 3.3 volt power supply and the same memory mix as the C542 but with fewer peripherals, and TMS320LC545, available with the instruction cycle time of 25 to 20 nanosecond, 3.3 volt power supply and the 6K watt of RAM and the 48 watts of the ROM. And TMS320LC546, available with the instruction cycle times of 25 to 20 nanosecond, 3.3 volt power supply and the same memory mix as the C545 but with P peripherals. So now the TMS320LC548, available with the instruction cycle time of 15 to 12.5 nanosecond, 3.3 volt power supply and the 32K watt ROM and 2K watt ROM. And TMS320LC549 versus VC549, available with the instruction cycle of 15, 12.5 and 10 nanosecond, 3.3 or 2.5 volt power supply and 32K watt ROM and the 16K watt ROM. Now coming to TMS320C 6th generation, TMS320C 6201, available with the instruction cycle time of 5 nanosecond based on the VeloTVeli C6200 fixed point CPU, execute up to 8 instructions per clock cycle and see performance of 1600 mega instructions per cycle at the rate of 200 megahertz. Contains 1 megabit on chip static RAM SRAM and 32-bit external memory interface XMIF, 3.3 volt input output and 2.5 volt CPU core. So TMS320C6701, floating point version of the TMS320C6201, available with the instruction cycle time of 6 nanoseconds based on a VeloCTVli 700 floating point CPU execute up to 8 instructions per clock cycle and achieve performance of 1 billion floating point operations per second, single precision, or 20 million floating point operations per second double precision, contains 1 megabit on-chip static RAM and 32-bit external memory RAM with the 3.3 volt input output and 2.5 volt CPU core. Now coming to TMS 320C80, so high performance 2 billion operations per second, 400 megabytes per second multiprocessor device with up to 400 megabytes of the on-chip memory, and the C80 offers 50 bytes of static RAM and can handle up to 64-bit instructions per TMS 320C82, a cost-effective version of the C80 without the video controller and with only 2 parallel processors and with some added features. So here the typical TMS 320 device family overview, starting from C2X and C3X, C4X, C5X, C54X, C6X, C8X and AV-XXX. And these are the typically D-Space digital signal processing and control engineering controllers with the starting DS1104 input output box with attached master input output ribbon, as you can see the figure here, and then DS1104RD controller board and DS1103 PCC controller board, then Microlobux BNC variants, Microlobux spring cage and Microlobux sub-D variant. So coming to D-Space controller DS1104, what it consists of: control desk from MATLAB, Simulink, can interface with DS1104RD R&D controller card, then it have a bidirectional feature with CP1104 connector panel, and then bidirectional with the power electronics drive board, and then can be interface to electrical machines as well as the encoder feedback. So this is complete block diagram of how the system works with the D-Space controller. And this is the typically D-Space controller control desk MATLAB with the Simulink interface, as you can see in the different parts as while you are implementing the power electronics circuits with the D-Space controller DS1104. So this D-Space controller DS1104, the DS1104 this R&D controller board is the standard board that can be plugged into a PCI slot of the APC, and the DS1104 is specifically designed for the development of high-speed multi-variable digital controllers and the real-time simulation in various fields. It is complete real-time control system based on a 603 power IPC floating point processor running at 250 MHz. And for advanced input-output purpose, the board includes the slave DSP subsystem based on the TMS320F240 DSP microcontroller. So for purpose of rapid control prototyping, specific interface connectors and connector panels provide easy access to all input-output signals of the board, and thus the DS1104RD controller board is the ideal hardware for the D-Space prototyper development system for cost-sensitive RSP application, and CP1104 connector panel provide the easy-to-use connectors between the DS1104RD controller board and the device to be connected to it. So devices can be individually connected, disconnected, or interchanged without soldering or via BNC connectors and sub-D connectors, and this simplifies system construction, testing, and troubleshooting. In addition to the CP1104, the CLP1104 connector or LED combi panel provides an array of the LEDs indicating the states of the digital signals. So here it is the typically technical details like main processor MPC 8240, power IC 603E core 250 MHz 32 kilobyte internal cache, and timers are one sample rate timer 32-bit down counter timer, 4 general purpose timer 32-bit and 64-bit time base for time measurement, and memory 32 megabyte synchronous DRAM and 8 megabyte boot flash memory for application, and interrupt control unit is interrupt that by timer, serial interface, slave DSP, incremental encoder, ADC, host PC, and for external and film synchronous interrupt. And analog inputs are 4 ADC 16-bit multiplex plus minus 10 volt input voltage and 2 microsecond sampling period, greater than 80 dB signal to noise ratio, 4 ADC channels of 12-bit with plus minus 10 volt input voltage range and 800 nanosecond sampling time greater than 65 dB signal to noise ratio. Analog output is 8 channel of 16 bit, 10 microsecond. Maximum sampling time with plus minus 10 volt output range, and serial interface serial USRT RS232, RS485 and RS422. And incremental code and phase is two digital input TTL or RS422 24-bit digital incremental encoders, maximum 1.65 megahertz input frequency, that is per default pulse count up to 6.6 megahertz, and 5 volt or flash 0.5 sensor supply, and digital IO is 20-bit digital IO by selectable direction plus minus 5 milliampere output current, and slave DSP subsystem Texas Instrument DSP TMS 320 F240 4 kilobyte word of dual RAM, 3-phase PWM output, 4 single PWM output, and 16-bit of digital IO TTL. So Microlobux, that is the next DSP by DSpace controller. Microlobux is ready to use rapid control prototype RSP system for the laboratory environment. It can be connected to the mains without using an additional power supply or a transformer. It provides the standard interface to the external device such as Ethernet or USB connectors for generating or measuring input or output signal. The board provides analog or digital input or output channels with included signal conditioning. So Microlobux consists of two boards, DS1202 and DS1302. DS1202 is the base board of Microlobux, which is based on the Freescale power architecture technology, and DS1302 is the input-output board of Microlobux. It provides the 4 standard input-output features. So DS1220 board controls the Ethernet interface, including the switch configuration for host communication and input-output access, and the USB interface for data recording and booting an application via USB mass storage device, and flash management for booting Microlobux and the loading real-time applications from the flash memory, and communication and data exchange with the DS1302 input-output board. So the DS1302 controls the analog input-output channels, the digital input-output channels, the serial interface RS232 and RS422/485, the CAN interface, two different sensor supply output, the customizable LEDs, the buzzer, and the resolver interface. The Microlobux OS typically consists of 4 front panel variants: top panel variant with BNC connectors, top panel variant with the spring cage terminal, and processor Freescale QRI QP5020 dual core, 2 GHz 32 kilobyte L1 data cache per core, 32 kilobyte L1 instructions cache per core, and 512 kilobyte L2 cache per core, 2 megabyte L3 cache total Freescale QRP10118 megahertz for communication with PC, and memory is 1 GB DRAM, 128 MB flash memory, and host typically interfaces. The host interface indicated gigabyte Ethernet interface, and it Ethernet real-time IO interface is indicated low latency gigabyte with Ethernet interface, and USB interface is USB 2.0 interface for data logging, flight recorder, and booting application for USB mass storage device, maximum 32-bit GB supported, and serial interface is 2 into USART or RS232, 42, and 485 interface. This CAN interface with the 2 CAN channel partial networking supported, LVDS interface, 1 into LVDS interface to connect with the programmable generic interface PGI1, and resolution and type 14-bit channels, 10 megabyte samples, say differential functionality, pre-running mode, 24 16-bit channels, 1 megabyte samples, differential functionality, single conversion and burst conversion mode with different trigger and interrupt options, and input output is -10 and +10. Resolution and analog output, resolution type, 16-bit channels, 1 mega samples, settling time 1 microsecond, output voltage -+10 volt, output current ±8 milliampere, and digital IO is 8 bidirectional channel, 2.5 volt, 3.3, 5.5 volt single rate functionality, bit input kilohm generation and measurement for 10 nanosecond resolution, pulse generation and measurement 10 nanosecond resolution, 4 into SPI master 12 bidirectional channels, RS432 485 type to connect sensor with differential interfaces, and electronics motor input out control functionality, separate interface 2 into 2 resolver interface, functionality of digital I/O channels. So 6 encoder sensor input, 2 Hall sensor input, 2 and that interface, 2 SSI interface, synchronous multi-channel PWM, block communication, computational PWM, and physical connection 4 into sub D50 input output connector, 4 into sub D9 input output connectors, and 2 into sub 50 connectors, and 48 BNC input out connector, 4 into sub D9 input connectors, and 2 sub input connector, 27 spring gauge box connector with the input output port, and sensor supply 1 into 12 volt, maximum 3 watt 250 milliampere fixed, and 1 into 220 volt, maximum 1 watt 200 milliampere available. These are about DSP. Now coming to numerical examples. So for TPS 54325 part, values given for data sheet, theta GA 44.5 degrees Celsius per watt and TJ max 125 degrees Celsius. Find PD max at different ambient condition of 25 degrees Celsius and 85 degree. Calculate linear loss factor for each degree increase in ambient. So PD max at 25 ambient is given 125 minus 25, so it comes 2.25 watt, and PD max at 85 ambient it comes around 0.9 watt. So derating factor is linear, so it is dissipation is 2250 milliwatt for a 100 degree rise from 25 to 125 degrees centigrade. For each 1 degree increase in ambient temperature, the power dissipation rating to be decreased from 2250 by 100, that's a 22.50 milliwatt per degree Celsius. So this parameter is used for calculation when power dissipation values are unspecified in the component. In coming to second numerical problem, in specific synchronous buck converter application where the input volt 5 volt, output is 2.5 volt at 1 ampere, 2.5 volt is delivered to the load, given converter efficiency of 90%, TCR value of inductor is 100 milliohm, and theta J is 75 degrees Celsius per watt. Calculate the device and the inductor power dissipation and junction temperature above ambient. So coming to the answer, the input power in this case is 2.5 divided by 9, so 2.75 watt, and the power dissipation in the converter is approximately 2.7 as 2.5, 0.25 watt. The power is dissipated in the inductor, which is external to the chipset, because the DCR can be known from the inductor data sheet. The inductor power is P inductor I out into DCR, that is 1 into 100 into 10 minus 3, so that's 110 power 3 minus 3, so that's 100 milliwatt. So device power dissipation is now 250 watt minus 100 milliwatt, that's 150 watt. So junction temperature rise of ambient is calculated using formula theta J into PT plus TA, that is TJ. TJ is calculated from here, it comes 11.25 degrees Celsius above the ambient or 75 degrees Celsius per watt in the thermal ratio. Coming to numerical problem 3, heat generated in the junction of diode at a constant rate of 10 joules per second. Thermal resistance data is as follows: theta S equal to 4 degrees Celsius per watt and theta CS is 0.5 degree Celsius per watt. Calculate the junction temperature of diode and ambient temperature 25 degrees Celsius. So answer temperature of heat sink surface is 10 into 4 plus 25, that is 65 degrees Celsius. Temperature of surface into 10 into 4.5 in plus 25, 70 degrees. Junction temperature similarly calculated 75 degrees. So diode should be selected above this junction temperature value. For TO transistor power dissipating 20 degrees, select the heat sink for the junction temperature not to exceed 136 degrees Celsius in any case of ambient temperature of 50 degrees Celsius. From manufacturer data sheet, theta J 1.5 degrees Celsius, insulated microwatt theta CS equal to 0.4 degrees Celsius per watt. So the theta CS equal to 1.5 plus 0.4, 1.9 degrees Celsius per watt. Temperature, now temperature different, 1.9 into 20, that is 30 degrees Celsius. Temperature at sink surface 130 minus 38, that is 98 degrees Celsius. Maximum permitted temperature difference from the heat sink surface and free air at ambient 98 minus 50, that is 48 degrees Celsius. And thermal resistance of heat sink to theta is 48 upon 20, that is 2.4 degree per watt Celsius per watt. Now coming to numerical problem 5. Coming to numerical problem 6, a string of 3 thyristor in series, each peak rating of 600 volt, use the resistor's value of 8 kilo ohm to force the more equivalent voltage sharing. Consider the worst case that one thyristor has a negligible leakage current and the other two thyristors have a maximum leakage current of 75 milliampere. What is the DC supply that can be combination? So here diagram is shown with the 3 thyristors in series with the voltage applied VDC with 8K polarization. So data of 3 thyristors, peak rating of thyristor 1600 volt and delta IV 75 milliampere, R equal to 8 ohm. So I leakage is 75 milliampere. So you can calculate VS equal to 3600 volt and combination can block 3600 volt. Coming to 7th problem, a 500 volt 30 ampere MOSFET modulates power frequency of 30 kilohertz from the 400 volt supply to load a whose resistance is 116 ohm. Design a polarized RC converter circuit to limit the turn of dV by dt to 1000 volt per microsecond. The turn on current 30 ampere. What is the average power dissipation in this number? So dV by dt is given 2000 by volt per microsecond and CS comes IL upon dV by dt, so it comes 0.0125 microfarad and Vs equal to ISR. RS comes from this 80 ohm and P equal to half CV C square VFS. This comes 30 watt. Coming to question number 8. H at VGC incorporating with the AC line voltage to rectifier of 220 kilovolt when the DC current is 1500 ampere, the rectifier delay is 15 degree and the inverter extension is 20 degree. Resistance of the line is 18 ohm, commutating reactance of the rectifier is 21 ohm and commutating reactance of inverter 21 ohm. Calculate the DC voltage and inverter terminals as well as the AC line voltage. So VLLR 220 kilovolt, ID 1500, alpha 15 degree, gamma is 20 degree, RL 18, XCR 21, XCI 21. So VDR equal to 1.31220 into bar into cos R. So it comes to 59.79 kilovolt and VAI comes with this comes to 29.79 volt and VAI equal to this. So we get VLLI 204.8 kV. Coming to in HVDC system for SCR 3.5, the S equal to 0.2, fire angle of 150 degree. Calculate the voltage regulation of the load rejection of the rectifier. So SCR 0.35, S equal to 0.2, alpha equal to 1. So ESI, EST 1 plus gamma upon SCR. So putting the value you get typically from here, the gamma equal to 1.61 and EST equal to 1.35, 1.375. So over voltage is voltage regulation 37.5. So 10 problem number 10, a 3-phase 6 pulse power factor corrected by 10 kW per HDC, also known GTO based current source converter with the following specification: input 54 volt per phase, 50 Hz, 3-phase supply, DC output to volt equal to 15 kilowatt with output voltage ripple less than 2%, determine fundamental AC current. So solution is ID equal to PD upon 15,000 divided by 220, 68.18 and IS1 PD into 3P and PF comes 19.6 ampere. These are unsolved problems. You can solve in the same manner. These are the references on which case we made. And thank you very much. Thank you.